David and many others have gone on to build other distributed systems and file systems and operating systems and now consensus protocols and like Stellar and so on. And what I wanted to talk about today is a set of ideas in peer-to-peer and distributed systems and secure systems that are really good and promising, but haven't kind of taken hold yet. So there's all of these really great ideas in research that make a ton of sense, but just for whatever reason get stuck in the R&D pipeline and don't make it all the way into production use. And sometimes there's good reasons for that, like, hey, actually the idea wasn't as good, or sometimes it's just not the right time, or sometimes there's no good implementation, or sometimes it's just difficult to shift the world, right? So content addressing is one great example of this. It made a lot of sense from the beginning and so on, but shifting the entire structure of the internet to go from location addressing to content addressing is quite difficult, and so you have to chip away at the problem for a while. So yeah, maybe let's just start with how do you think about R&D and just maybe how you approach research ideas and producing work, and then how do you want them to get fleshed out and productionized in the world?
Okay, well, there's several questions there. So how do I approach R&D? Well, so I have the luxury being at Stanford of being able to work with super smart people and do whatever I want. So the question is like, what should we do? This is kind of a blank slate. And I always come down to the kind of the same three questions when like we have an idea or like a student approaches me with an idea. It's, why would anyone want this, right? There's stuff that like you think it's good, but then you dig into it and it's like, actually, you wouldn't ever use this in practice, right? So that's one. Why would anyone want this? Two, is there any chance that we can actually pull this off, right? Like I could come up with some amazing sounding thing, but like if it's actually impossible, our chance of success is zero, then it's not worth it. And then the third question is just, okay, let's do the really half-assed thing and like try to solve it with like today's existing ideas. Can we get 90% of the way there? Like, why isn't the kind of the half-assed solution good enough? And so once you answer those three questions, then you can kind of identify an idea that's maybe worth putting time into.
And once you identify those ideas and you put some time into it and maybe get some research results, how do you then go to getting that thing adopted? Like, do you kind of, if you were to, I'm sure that you can think of so many ideas that are just sort of stuck in paper form but haven't made it. How do you sort of arrange the pipeline to get some of those ideas built out faster?
Yeah, I mean, so particularly as an OS researcher, backwards compatibility is kind of like the number one impediment to getting stuff out there, right? You can build a brilliant new operating system kernel, and if it doesn't run a web browser, you're not going to have a lot of traction, say, on people's desktops. So the answer is try to slice the problem up in such a way that you don't have to solve everything. And so one way to do that, in taking the example of operating systems, is look at new kind of emerging areas, right? So maybe like it's too late for the desktop, but maybe like you don't care. You don't need backwards compatibility for like whatever's running the embedded processor on your fridge, and so like you can kind of like use the new area. We tried that with like cell phone operating systems, but that turned out to be a failure because it was just too hard to like figure out what was going on in the baseband layer. But maybe there's other areas. So the other thing you can do is try to make the problem easier. And so we had this project, my then student, Adam Belay, who's now a professor at MIT, did this project called Dune. And the idea of Dune was, let's use the virtualization hardware in x86 servers to not implement a virtual machine abstraction, but to implement a Linux process abstraction. So basically, you run a Linux process, but it's running in basically it's running in the kernel mode, but like of the guest mode of the CPU. And if you use a VM call instruction, you can actually get a Linux system call. And so because the problem with operating systems, right, is you have like a brilliant idea for like how to redo the network stack, right? And so you implement this, and then to make it useful, you have to implement a file system, and you have to implement, a windowing system or whatever. And so here, the idea is that you could do just the part that's interesting, like just redo the networking stack, say, and then if you just need a file system, you could just kind of pass that through and use VM calls. And so you can literally like call printf in the middle of an interrupt driver, and there is a standard output. It's like connected to the standard output of that Linux driver. So that has been like really useful. There's been a bunch of research projects that managed to use Dune, and it made their lives a lot simpler. So, but sometimes it's like, sometimes problems just like require a huge effort, right? But I think often you can figure it out. The nice thing about being at the software and operating systems is often you can figure out how to do it with less effort. If I were like building, new VLSI chips or something, I might need to like employ an army of 10 grad students and work for a bunch of years to have something that's not competitive. But
yep. And when you think about like the range of work that you've been doing, so from again peer-to-peer file systems, operating systems, consensus, and so on, there's probably a set of ideas there that you thought like really were really great ideas that just haven't made it through. Can you maybe mention 2 or 3 of those ideas, and we can like dig into them?
What are great ideas that have not made it out there? I don't know. I mean, there's sort of principle. Well, there's principles, and then there's ideas. So there's like technologies that I wish were out there, and it's just unfortunate that they aren't. I mean, just an example, not that I've contributed in this area, but like password authenticated key exchange, right? To me, it's grotesque that we're typing passwords and like sending them in clear text to servers, right? And like we literally have better solutions than this, right? Even with passwords, right? Like, of course, a lot of people now are saying, oh, passwords don't work, get rid of them. But actually, we could do passwords better. And the thing that's standing in the way of that, like I had a student, Quinn Slack, who did a really pretty tasteful implementation of PAKE, which is password authenticated key exchange in the browser. And we went and we talked to the people at Mozilla, and they said, well, the problem is that people who are building websites want to have control over like the failure path if you type the wrong password. Yeah, and it's true. Like if you were using passwords right, then when you mistype the password, you would learn one of 2 things: either that you're talking to the wrong website or that you typed the wrong password, right? And so that would give up some control, but the benefits would be immense. But like it's just people are unwilling to give up that the small advantage that they currently have in exchange for like a much bigger advantage. In terms of principles, though, I would say, there's sort of principles that guide my work that cut across a lot of areas. And one is that, like, I really deeply believe in sort of egalitarian interfaces and APIs. And one of the things that's a really unfortunate thing that you can do in a system design is have basically sort of privileged and unprivileged programmers, users, software have access to kind of qualitatively different APIs, right? Because then you get this thing like on Unix and Linux where essentially root is like the garbage can, and there's all this stuff that like, for example, there's protection built into Linux, right? It's called user IDs. And yet applications can't use user IDs for the most part to like sandbox themselves, because it would be like more of a pain to install them, and it wouldn't just like work. You'd have to like create a new user ID and stuff. And so we do other things to kind of sandbox software, and we're like giving up the ability to use the hardware to do that. So the principle would be like instead try to make it sure that like privilege is like a quantitative difference, not a qualitative difference, right? And that's certainly something that we've taken to heart in like the work at Stellar, where what we're trying to do is make sure that any random person who wants to innovate and a big bank have access to like the same APIs, even if they have sort of different assets. So like there's just more ability to innovate. And then I guess the second principle would be I don't know, I guess you could call it like the weight and balance principle. I'm not if you're designing an airplane, like you can't lard it up with too many features, because like if it's too heavy, it's not going to fly. And unfortunately, we've kind of lost that with software, right? You just kind of pile in the libraries and whatever. And so, and the other thing people do is just throw more engineering effort into something. And it's easier to kind of write code than delete code. And one of the things that is, you see say at Stanford, where like we're working on research in small teams, you have to make these design decisions of, okay, we're not going to like build every feature. You really have to decide what the core features are. And at the end, like I much prefer these like stripped down tools that do the core interesting thing and don't try to do everything all at once. I guess if I could add a third one,
Yeah,
if you're designing systems, think about the graph of like the number of hours of experience people have with your system or as developers using your platform, and the sort of power that they have using it. And what you want to try to do is, have a high y-intercept, but also like a kind of constant slope. And these systems, like say C++ is a programming language where like to really do stuff, you need like 2 years experience. Like that's kind of like there's something wrong with your design if that's the shape of that graph.
Yeah, how does that apply to, say, software libraries or I guess, yeah, C++ makes sense. You have to learn an enormous amount. Python, you can get started really quickly and already leverage a lot of power. How do you see that kind of applying in the design of software where does that go into API design? Does that go into like feature set design or?
Yeah, it goes into API design, and it also goes into tooling, right? One of the things, like I spent a fair amount of time at Stellar, which is the blockchain I'm involved with, doing stuff that's not super research worthy, but like implementing like a kind of an assembly language for Stellar transactions. Because it looked like there are people who like either you're really advanced and you're implementing to like our Go APIs, or you are like basically using a wallet, right? And there wasn't like this sort of gradual. If you wanted to just write a script to like generate a bunch of transactions, it was like a pain to do that. You'd actually have to write a Go program. And with my silly tool called Stellar Transaction Compiler, you could suddenly write like shell scripts or just simple command lines to basically like generate transactions to kind of try to fill in that gap. So I guess look at sort of the gaps in like people who have like 15 months of experience with your system, like what can they do, if they aren't experts? And if there's like kind of a trough there where there's not like a payoff, like find ways to like fill in that area, and you sort of create a smoother on-ramp for people to like use and become experts in your system, right? You got to get those endorphin rushes, right? When like, oh, I did it, it works, right? Like that's what motivates a lot of us developers, right?
Let's dive into content addressing. So there's actually a question that I've never quite been able to figure out. Where did the idea of hash linking in file systems start? Because I've traced it back to SFSRO, which it did, and then probably before that, like Fossil and Venti in Plan 9 in Bell Labs, like already had the beginnings of that, but like you interned there for a while. So I was wondering if like you brought that idea or like you learned there, or?
I think SFSRO might have predated Venti.
Cool.
But yeah, I remember specifically. So for my dissertation, I'd done this file system called SFS, self-certifying file system. The key idea, then again, following the principle of like filling in the gaps and making the system more accessible, the idea was to embed the public keys of servers in path names, and then certificate management would just be like creating a bunch of symbolic links, because a certificate is just a way to assign one human readable name to a public key. And so rather than learn how to, fill out like an X509 certificate request or whatever, like everybody who can do a little bit of shell programming understands what a symbolic link is. So it was like just much easier to do that. But if you did that, a certificate authority just became a directory full of symbolic links, assigning human readable names to these other path names that contain public keys. And so we built, of course, then if you want your certificate authority, of course, in order to be secure, you need to have the signing key be offline. So we had kind of two dialects of the protocol, a read-write where the server was online, and then a read-only where the stuff was signed. And so kind of the first version of the read-only, we kind of signed all the different pieces of the file system individually. And then I remember I was, talking to my advisor, Franz at the time, and I was like, and he was talking about how we were gonna like redo this. I was like, no. I've got the way we're gonna redo this, much simpler. There's only gonna be two RPC calls. One, get me a digitally signed message that contains the hash of the root directory. And two, here's a hash value, get me the pre-image. And like, that's all you need server side, so we can make the server side super simple. And that's what led to SFSRO that I think was in like OSDI 2000. So I think I was like a little bit before Venti.
Yeah, and that's the core hash linking for data that then, IPFS and Git and so many other things are based on. So, I think we're still in like the quest of adding content addressing to the network. Like we're now 10 in the 10 to hundreds of millions of people benefiting from this, but not yet billions. We'll get there.
Yeah.
But as you think about like that set of ideas of kind of hash linking is this extremely powerful primitive, and yet it's 2022, and so many systems out there are still kind of linking to all this mushy, dynamic, not certified, not authenticated data structures. Like what has gone wrong over here, right? Like why is it? Is it too hard? Is the idea too complex? We sometimes talk about it as like people have to go through their Merkle journey of understanding how everything is. When you hash link everything, everything gets better, and you can move everything into different spots, and you get all the security properties and distribution properties. And that idea space is, for whatever reason, not as prevalent as, say, something equally complex like encapsulation in protocols and the protocol stack in networks, or reliability in reliable transport. So like all these ideas are kind of seem equally complex, but for whatever reason, hash linking isn't quite there. So I don't know if you've
Yeah, I mean, it's not just hash linking, it's also key management. So I would say one thing that's a little bit unfortunate is the design of TLS and how it's used in practice. So the problem with TLS is that it's providing two totally different things. One is it's actually providing security at the transport layer by encrypting your communications, and the second is that it's kind of most of the implementations build in this like X509 certificate stuff. And what you really would like to do is kind of disaggregate these things and be able to kind of authenticate both contents and endpoints in different ways, right? So like a problem with the web is that you can't name a public key, right? It's like you can do this key management in X509 and get your HTTPS URL, and then you can get a web page, which is a bunch of HTML, but then you can't use what you get back to actually name another public key, right? So the key management can't be part of the system itself, and it doesn't have this like self-referential property.
We have blockchains now. We could do a lot of the key management through like just putting all the certificates on chain.
But I'm saying like the system that everybody, that, a lot of people use blockchain, but way more people use the web. And sort of like the thing that like is probably many people's first experience of the internet now is like using web browser, just doesn't have the flexibility to implement your own key management or content authentication.
As you think about like blockchains and where they might go, like not just kind of the public large-scale cryptocurrency blockchains, but just in general, this idea of using consensus with hash linking and maintaining these logs. You could redo the CA system this way. You could redo DNS this way. You could redo. You could have like secure time this way. How do you see that kind of like syncing into the network stack?
Well, there's this classic paper on end-to-end arguments in system design, right? Which says that if you can implement functionality in the network or kind of closer to the end nodes, you should do it in the end nodes. And I view kind of a lot of systems design, throwing in a fourth principle here, as kind of keeping in mind a more generalized version of that, which is you don't just have end nodes in the core of the network, but you have sort of routers that are closer to the user and that the user has more control over. Within an end node, you have stuff that you could do in the kernel versus stuff you could do in a library versus stuff you can do in the application. And so kind of, the more you can move that functionality out, say, towards being in a library, I think the better. So the question is, should content addressing replace IP? I think probably not.
Not IP, but HTTP, for example. Like just pulling some. Today you use HTTP to pull content, and you ask for a file path, and you get back some bytes. And maybe you should ask for a path, get back a hash, take the hash, get the file.
And so your question is, how should that sync into the network core? And so I think maybe like an interesting open resource question, and I do have a couple of students at Stanford who are thinking about this, is that a lot of these DHTs that you can use are not Byzantine fault tolerant, and building like a fully decentralized Byzantine fault tolerant distributed hash table seems like a very hard problem. And so the question is, if we could ask a little bit more of the core network, could we actually do better? And
as you think about DHTs, one of the things that we've run into is just the speed. Like when you want to use, so in IPFS we use a DHT, when we use Kademlia to do the discovery, so the content routing part of the problem. So if you have a hash, how do you identify what nodes in the network have the content so you can go get it, right? We call this providing, so content providing. We create these provider records, we put them in the DHT. A user trying to look it up looks at the DHT, gets a provider record, can go and find them. But DHTs have a little space per node, and then they have really large round trip time distance to all of the nodes. So traversing these DHTs gets really expensive when you want to do something like a page load, right? So if you want to do a page load and you have 100 resources and you have to touch a bunch of different nodes, suddenly it gets like super slow. Have you thought about like how to either make DHTs incredibly fast so you can get close to O of 1, or how do you, or end up with DHTs that are a lot smaller? So one route is this content indexing pathway where we've gone, which is instead of having, say, hundreds of thousands or millions of DHT nodes, have tens to hundreds, but make those nodes extremely large. You have some security between the decentralization of those nodes, but you now have tons of records in a smaller set of machines. Which of these pathways do you think we're gonna, can we like hack like the massive scale DHT systems with like millions of nodes and kind of somehow solve the speed of light problem? Or do we really want to go for like tens to hundreds to maybe thousands of nodes in like interconnects in data centers and make these massive routers there?
Well, first of all, are you sure it's a speed of light problem? Because I've seen Kademlia, I've heard Kademlia was taking like tens of seconds or whatever. So.
It's speed of light when you have millions of nodes and you don't yet have a secure communication set up, a secure channel, you end up in this problem where, hey, if you want to get the information from the next party, you have to then establish a new secure connection to them. And so that ends up with a bunch of round trip times.
Well, why does it have to be secure?
Because of privacy reasons. You don't want to necessarily tell everybody. So two parts. One is you don't want to flood the network. So you want to do iterative discovery, which is slower. If you do recursive, you then need some other incentive structure in the DHT to make sure that you don't flood it. And then second, you want privacy in the queries, and you want to be careful about who you necessarily convey what information that you're looking for.
I don't know. I guess I would push back on that assumption a little bit. So first of all, like it depends what you're using, right? You could certainly implement a custom protocol that would require fewer round trips. And
so you would want
to design the protocol such that you can overlap the latency of like some of the encryption with with network communication. But I think that, I mean, what are these things? Using like TLS typically, or
yeah, there's a set of different, so TLS and noise and other.
Yeah. So I think I would probably first look at the low-hanging fruit, which is if you were to design a custom protocol, and
to try to like do the encryption such that it's not on the channel of communication, so you're doing requests in the clear.
Yeah, and so that you can, I mean, the other thing is you could use like, suppose when at the time you learn of like a node's ID, you also learn of like, it's a public key. You could potentially do like a non-interactive Diffie-Hellman key exchange. So you basically like can send the thing encrypted, right? I mean, that's not, you lack forward secrecy there, but I mean, given that we're talking about a kind of level of casual, this is only going to work against a sort of casual attacker who's like eavesdropping on the Wi-Fi anyway. So you have to kind of find the right balance. So anyway, so the point being that already we're talking about stuff other than speed of light. Right?
But the way this connects is that you have these problems that add another round trip, and when you have other round trips and you're trying to traverse a very large, you end up in this sequential problem where you have to like find out a bunch of information, and in order to find out the information, you have to
I understand. But what I'm saying is that it's important to say that these round trips aren't like this experience. The performance bottleneck isn't the speed of light; it's other things. It's like node failure, right? Why is node failure? What's probably like the number one cause of node failure? Well, like what a nightmare NAT traversal is to implement, right? So if you were to sort of, in terms of what could you ask from the network, it's like, well, start rolling out IPv6 and have some range of ports that like applications can use that are basically not firewalled. So like these are things that like you could ask from the network. and I think that you could do okay. I mean, I guess, should we go to a world where there's 100, data centers that are storing the world's content? Like, that's one possible world. I don't like that as much because there's centralized control. So I'd like to exhaust all the other.
Well, you could put them in kind of you could look at the grapevine of the internet and put these wherever there's some high connectivity in the pathways, right? So if you look at the tree structure and you put in content routers in the vertices that have lots of downstream parties, then kind of increase the amount of content there. Because storage is getting super cheap, right? Like you can have these things are going to carry terabytes now, and then it'll be tens of terabytes within not too long. A server rack is now a petabyte. So like you can put a petabyte of records into your basement, or a petabyte of records into this building, and then suddenly have this massive content router.
Yeah, I mean the retrieval bandwidth is potentially an issue. I think the problem with this is that, like, if you could wave the magic wand and have ISPs deploy this stuff for you, that would be great, but it would be set in stone, right? Like trying to get them to upgrade it then is going to be like a big deal. And so so it is, there's an argument to be made that, like, okay, maybe, if Ketchuk is like the, SHA-3 is like the hash to end all hashes. So we're happy to like just commit to that and like do this. And maybe the interface is simple enough that we feel we have something that like is the right thing. And so we're ready to like bake it in stone.
Just make upgradable protocols.
I'm a little more, I'm a little wary of that, right? So I'd want to know, like, want to make sure that it can't actually happen at end nodes where like we could have like competing versions of the protocol if necessary.
Yeah, no, so I mean, instead of committing to Ketchuk, you just add a byte ahead of time telling you that you're going to use which hash function you're going to use.
Yeah, you want crypto agility, but like getting people to like rehash like, petabytes of data, like they're not going to be that excited about that. It's like having a flag day where like you switch, or having to, it's just, it'll be annoying.
We already have it in IPFS. So in IPFS, we use SHA-256, we use Blake 2, and we use a bunch of other hash functions. And it's already kind of all integrated, so you can navigate through the pathways, and then you just disable hashes as they break or they get weaker. But,
so maybe we're at a point where if you could like basically commit to your software and say like, I'm comfortable never upgrading this again, modulo minor bug fixes, like you'd be happy doing that. And so then you just have to make the argument that show that it's like the benefit you get from pushing into the network is worth the lack of upgradability and the lack of competition from other potentially.
Let's talk about privacy for a moment. Like as you think about preserving privacy in reader and writer paths. So writer privacy is hard, reader privacy is way harder. When you kind of like think about how to make content publishing and content viewing properly private, of like all of the approaches that you've seen tried, what do you think is the most promising?
I'm not sure, because there's a bunch of different approaches, and none of them is ideal, and they don't really compose, right? So like private information retrieval, for example, is really cool, but it's really expensive on the server side. So another thing you do is you could like say split trust and say, well, these two organizations would need to collude to figure out what I'm looking up, right? But that's not a great thing either, right? And then you can do sort of half-assed things where you have at least plausible deniability because you're fetching something random, but like statistically, people are still going to figure out what you're doing. And so I don't know, because like none of these are really perfect.
I mean, the servers are pretty fast now. We're talking about using zero knowledge, and in 5 years we'll be using 10 years we'll be using fully homomorphic encryption. Like
no,
stuff
but
is
like super
for private and for truly private information retrieval, basically it only works if the server touches every single piece of data, because if it doesn't touch every piece of data, then it knows that you didn't fetch a particular record. So if you want perfect privacy, like there's no way to do it in order log n.
Surely performance is going to get past the amount of like humans, and so like you only have a certain amount of data that you're generating at one given point in time, and so only some amount of data that you're trying to look up.
I think the amount of data we generate might be proportional to the number of devices we have.
No, I mean like the lookups that you might be doing. So so a human does a certain amount of lookups, and sure, that might increase on some
Sure, that's
function.
fine. But my point is that the cost of the lookups with private information retrieval increases with the size of the data. So it's the amount of data times the number of people making requests.
But you can probably add some kind of structure to this to break down the problem, right? So you could like do some like bucketing first, and then private information retrieval within some buckets.
Yeah, so maybe, and then you have to look. But so that's my point, right? That there's all these trade-offs, and another thing you could do, like you also have to think about censorship resistance. So one of the things that we did, I had a student at NYU, Mark Waldman, he had built a system called Tangler, and the idea was that all of the data that was stored was kind of information theoretically unrelated to the content. So you would like basically fetch multiple data blocks that actually, depending on which ones you fetch, could reconstruct different documents, and then just reconstruct the particular document you want. But of course, there's like a 3x overhead in bandwidth for doing that.
Well, 3x is not terrible.
Yeah,
that's pretty good. So one thing, so we're at lunch now. So David has kindly agreed to do office hours with folks here that are doing distributed systems work and working on content routing or DHCs or CDNs or hash linking and so on. So right after lunch, we'll go to the terrace or somewhere up there. And if you're interested in like talking about some of the problems that you're working on, some of the tech that you're building, and get feedback from David, we'll do that. We'll kind of just keep it to like 5 to 10 minutes, and then so that other people get that. And yeah, after lunch, I'll take maybe 2 questions from the audience, and then we'll stop for lunch.
Hey, good afternoon. So I landed in the talk about private data retrieval. I'm very interested in, I imagine you could mix data, right? You could mix data from various sources. So it's like, this one file has information from 5 different sources mixed. And then you can request a bit from one server, from another server, from another server, and the specific combination of data that you retrieve from various servers could be reintegrated into the exact data you need, and that way none of the servers you request
Yeah, I think
data
that's
from.
the Tangler.
Yeah. So that was the Tangler idea. And so there's kind of 2 things. There's one, the fact that all the data is tangled up. So when you request blocks, those blocks could be used to reconstruct multiple documents. It doesn't say what you're doing, and you couldn't sort of censor a document without causing collateral damage to other documents. And then the second part of it is you need to have a way of kind of shuffling the data around such that if a server cheats on even one block, one data block, that like they can get sort of kicked out of the system, and such that nobody is sort of permanently responsible for any block, so that even if someone is being bad, like eventually like it'll move to other places.
Yep.
I guess you would also have to make sure then that not all the nodes that you request data from are owned by the same party, and this is a tricky part. Now, how do you prove that these are different people hosting your stuff?
Yeah, I mean, so that depends on kind of the system design and what are the guarantees that you want to preserve. Like, and sure, you're going to end up with many nodes involved in the protocol.
You can check out our Tangler paper. It was from like 1997 or something, but from.
But by the way, just tons of amazingly good ideas are in the literature. Like, just have not been implemented for some reason, or have been, but like got stuck somewhere in the R&D pipeline and are waiting to be distributed. All right, final question. Just raise your hands.
You talked earlier a bit about the sort of combining Byzantine fault tolerance with distributed hash table. Could you talk about I guess the security model that Kademlia or distributed hash tables have right now, and how Byzantine fault tolerance comes into play?
Yeah, I mean, it's basically not good. So we don't really have a good solution to this problem, right? So people can do things with sort of admission control to try to prevent Sybil attacks, but it's fairly unsatisfying. And my then student, Michael Friedman, who's a professor at Princeton now, he built this thing called the Coral Content Distribution Network. And the goal was always to open this up to a bunch of, and let anyone participate. We never ended up doing that, and in part it was because we couldn't trust the nodes, right? Someone could mess it up, and it was that, and the fact that you couldn't authenticate content in HTTP in HTML, because what you really want to do is fetch content from this caching layer and not have to trust the caching layer for content integrity. And just because, again, the browsers aren't designed in the way that I wish they'd been designed, you can't do that very easily.
Yep. Well, thank you very much, David. Thank you for being here with us and sharing the knowledge.
So what, 1 p.m. Terrace? Or?
Yeah, 1 p.m. in the terrace.
Okay, yeah. Maybe see some of you then.
Thanks so much.
Thanks.